This screencast is going to be a review from first year chemistry, hopefully, where we talked about things like entropy and free energy. So this first section talks about what does it mean to be spontaneous and what is the definition of entropy. So spontaneous they've defined as a process that occurs without outside intervention. Now that means that it will take place, but it doesn't say anything about the kinetics of it. It could take a billion years. The decomposition of diamond into just regular graphite is actually thermodynamically favorable, but it happens over billions and billions of years. So luckily our diamonds are not just turning into graphite. So the other piece that I think is difficult for students is talking about, well, what does spontaneous really mean? So even if I think about burning gasoline, that will spontaneously happen, but you still have to have that activation energy, that amount of spark, in order for it to take place. So it doesn't mean, like spontaneous combustion. You still need to provide that amount of activation energy. All right, so in general, entropy gets the symbol S. U is taken by a lot of different things. So it's just the measure of disorder in a system. So if you focus on that word rather than order, I think it'll help you kind of keep straight what entropy is. And honestly, some of these questions that they'll ask, you'll think, really, is that all I have to explain? And that's really just making sure that you understand what S is and what disorder is. So in general, gases tend to have really high entropy because they have a lot of disorder, and that's because of microstates. And you don't have to mention microstates, but those are positional probabilities of where you're going to find either atoms or molecules. And so if you think about a gas particle and all the different places that it can occupy, there's going to be a ton of microstates or possible arrangements for a gas. So this first thing, we're just kind of practicing which has more disorder and then explaining your answer. So between solid phosphorus, which would be P4 solid, or phosphorus in the gas form, which one would have more disorder? And so we know that gases have more microstates, so it would have higher disorder. All right, this one's asking you to look at the same substance, but at two different pressures. So this one's low pressure, this one's high pressure. So if you think about what the one at low pressure is going to be able to do that the one at high pressure will not, this one will have more freedom of movement, right? So the one at lower pressure is going to have more disorder or more entropy. And then the last, we've got an ionic compound in its pure form, and then we have an ionic compound in water. So just the fact that you've got KOH now mixed with another substance, that's going to give it more disorder. But in addition to that, we know that this breaks down into ions, so the aqueous is definitely going to have higher positional entropy or more disorder. So we also talked about a change in entropy. So change, given delta S, we always find it when we're doing anything thermodynamic related, products minus reactants. So if we're going from a more ordered state to a less ordered state, delta S is going to be positive because you are decreasing the amount of order, which is increasing the amount of disorder. For this one, if we go from less order to a more ordered state, so think about like your room or your house maybe being messy, going to a more ordered state, that change in entropy is actually negative because the amount of disorder is decreasing. So keep it in terms of disorder, and hopefully that'll help. Okay, so we're going to predict the sign for delta S. So what's happening? So if it's positive, we are increasing disorder. If it is negative, we are decreasing disorder. Okay, so going solid copper sulfate is being added to water. So we've got CuSO4 solid being put in water. So we know it's going to go into ions. So this side has less disorder, this side has more disorder. So our change in entropy is going to be positive. Water vapor condensing. So we were a gas, and now we're condensing to a liquid on the side of a glass. So if we think about the change in disordered, we were very disordered, now we're less disordered. So this would be a negative change in disorder. Dry ice subliming, so that's CO2 solid going directly to CO2 gas. So think about what you've done to microstates. This is a pretty ordered system. This is a very disordered system. So we have increased disorder, so that's a positive delta S. And then O2 gas being dissolved in water. So this is interesting because if you look at this example and you're not really thinking about, what's happening, you think, oh, well, this one led to more disorder. But you're taking a gas now and shoving it into a liquid. So it's dissolved oxygen, which happens, in how fish respire. But now you have taken it and put it into water. So you have much less disorder. So you have decreased disorder. So this would be a negative delta S. So if you've ever wondered why it seems like things get more and more disordered, this action certainly does, because you guys know I like order. The second law of thermodynamics tells us why. So we are heading towards an increasing amount of disorder. So first law of thermodynamics, remember, was energy can't be created or destroyed, only changed in form. This one is saying, look, the universe is heading towards more and more disorder. If we want to keep it ordered, then we have to put energy in order to make that happen. All right, so a pretty simple idea of what's happening. Remember our systems approach to thermodynamics. We need to, focus and really well define our system, and then everything else is going to be surroundings. And when you take your system and add it to your surroundings, that's when you get the universe. So we did the exact same thing with delta H earlier in the year. All right, so the ones that tend to be spontaneous are the ones that have a positive delta S. And that matches the second law because we are heading towards more and more disorder. The ones that have negative delta S's will still be spontaneous, but it's going to be in the opposite direction. So like if I go back up to this one, right, oxygen is going to spontaneously come out of water because that forward reaction is the non-spontaneous one. This one is. So if we look at what's happening in these examples, and sorry, I've skipped over delta S equals 0, but that means you're at equilibrium. Forward and reverse reactions are both happening at the same rate. All right, so if I look at this, they want to know whether the following reactions will be spontaneous and then give the sign for delta S. So if we look at what's happening, we have 2 moles of gas forming 3 moles of gas. In addition to that, I've now separated the compound. So we have more disorder on the product side, so it will be spontaneous in the forward direction. And then here we've got 2 separate things. They didn't give the physical states, so let's just assume they're gases. That way we have something to work with. So we have 2 separate things forming 1 compound. So this is heading towards more order or less disorder. So this one's going to have a negative delta S and tend to not be spontaneous. So we would label A as spontaneous and this one as non-spon. Now we are only focusing on this one delta S piece. If you remember, we really have to put it together with the enthalpy term, the delta H term, as well as temperature. So this is just kind of one way we're going to predict spontaneity. We're going to get to Gibbs free energy where we can calculate it overall. All right, and then practice 4 is just probably the simplest math we've done all year. Just adding your system and your surroundings. So this one is telling you that the system is becoming more ordered, right, because it's a negative. So we'll add the negative 27, and then the surroundings is the one that's gaining that disorder. So again, record keeping, which way is it going? So we end up with 13 joules per Kelvin. So the overall would be, we would say, spontaneous. That's in terms of our S universe. All right, for this one, we've got delta S equal to 70 plus a negative 85. Okay, so our system and surrounding. We get a negative 15 joules, and so that would tend to be non-spon. Again, only looking at that delta S term and not putting it together with delta H and temperature quite yet. Okay, so this is certainly difficult to talk about delta S of surroundings, which is why we tend to focus on delta S of the system. But in general, we could say that exothermic reactions tend to be spontaneous, and endothermic reactions tend to be non-spontaneous. Okay, that's just in general. We can connect delta H and delta S by putting it together with temperature. So this relationship doesn't come up a whole lot on the AP exam, but when we look back here, we're looking at our sign of delta S, right? And we see these units. It has units of joules per Kelvin. So that tells you that delta S, or the entropy term, is temperature dependent. So the temperature is going to change the value. So hopefully it makes sense that delta H is typically given in kilojoules. Temperature would need to be in Kelvin, and we can divide. Okay, so that kind of connects those two. So in practice 5, they want delta S surroundings. So keep in mind that over here, delta S surroundings, they're making it the opposite sign because typically delta H is in terms of your system. All right, so if I want to know what delta S is, I'm going to take the opposite sign. So the forward reaction is exothermic. That shouldn't surprise us because it's combustion. I'm going to make it positive, so that's kilojoules. And then 25 degrees Celsius is going to be 298 Kelvin. So we'll divide it by 298. And for this one, we get 6.86 kilojoules per Kelvin. So that would be a positive delta S for the system. So this would be spontaneous, which is what we would predict once we provide that initial spark. Okay, I'm going to let you practice B and C and see what you get for those. This one comes out to 1.06 kilojoules per Kelvin, and this one negative 0.15 kilojoules per Kelvin. So spontaneous, non-spontaneous, both are close to, crossing over at the 0, so not a huge difference there. All right, so the last thing we're going to talk about is what is Gibbs free energy. So this puts, the question, will it be spontaneous, into a final calculation that you can do. So if you are ever asked to comment on whether a reaction will be spontaneous, it's fine to talk about the fact that exothermic reactions tend to be, and ones with positive delta S tend to be spontaneous. But Gibbs free energy is the final say on whether a reaction will be spontaneous. So if you're given data, make sure you're using it appropriately. All right, so this puts together, how do you find Gibbs free energy? Well, it's a combination of the enthalpy term, which we've dealt with this year, and then T, which needs to be in Kelvin, and then our delta S term. And that's typically in joules per Kelvin. So you need to make sure that you're going to switch that to kilojoules per Kelvin. It's a common math error that students make. All right, so we'll do the first one together, and then I'll let you practice. So here they give you 40 kilojoules. They give you 300 joules per Kelvin. So we're going to change that to kilojoules per Kelvin. And your temperature is already in Kelvin. So let's just kind of speculate. We've got an endothermic reaction. We have one that is increasing disorder. So this one could go either way, right? It matters whether the delta H term is going to take over this, whether the delta S term is going to be able to overtake this. Because this tends to be non-spontaneous, but this tends to be spontaneous, right? So the question is, at this temperature, are we going to be spontaneous? So delta G is equal to 40 minus the 130 times the 0.3. So our final answer is going to be in kilojoules, and we get 1 kilojoule, which a positive delta G means non-spontaneous, okay? But that number is pretty small, so we're pretty close to kind of crossing over, right? So if we look at this one down here, you'll notice that they've upped the temperature a little bit. So I want you to calculate B and C. Just pause the screencast, make sure you can get those numbers, and then check your work. On this one, you should have gotten a delta G of 85 kilojoules. So this one is non-spontaneous. And this one is going to be less spontaneous than that one because of that magnitude. So the magnitude does tell you how close is it to being spontaneous. So this one's further away from spontaneity than that one is. And then down here, we have negative 85 kilojoules. So they've switched the sign, right? Negative delta H, those tend to be spontaneous. And you have increasing disorder, those tend to be spontaneous. So this one has both things going for it, so it would be spontaneous. All right, so you're going to try the practice problems from the textbook, and then we're going to kind of, at our next lesson, put this all together. So even if we don't have numbers, we can kind of predict spontaneity.